All right, let's get started here. Homework 9 should be submitted tonight before 11:59 p.m. So that's the deadline, not after that. Phase 2 of your project, which is a pair of maps of the network that you've designed, that needs to be uploaded before class on Monday. And just to further explain what those two maps are, it's the same network, so you're going to only have one pipe network, but I want to see how that network is performing under two different conditions. One of the conditions is the maximum design flows at each of the locations, each of the junctions. And then the other map should be how the network is performing with zero flow rate. So the same network, two different conditions, and so it should be annotated where it's showing the pressure and pipe diameter and all the details that were explained in the handout and in the previous illustration that I gave you in class. Looking a little bit further to the future, on Friday of next week you've got homework 10, which will be due, and I've just uploaded that to Blackboard. If you look at the assignment handout, I've put the answers to each question on the assignment handout just to give you an idea if you're doing it correctly, because you'll submit that assignment at the same time that we begin our midterm exam. So you wouldn't have gotten any feedback yet on the homework, and I want you to feel confident that you're doing those problems correctly before we head into the exam, which is a week from today. Does anybody have any questions about these announcements or the schedule over the coming week? Yeah.
For the zero flow rate, you just, on the junctions, do the outflow as zero?
Yeah.
Okay.
You go back into the demand collection, and all the locations that you previously had defined your flow rate, you just go back in there and you zero it out. So you may want to create like parallel files, like you have your network with the design flows, and then you save as, and you say same network but zero flow rate, so that you could go back to the first file without having to type all the flow rates back in again. I mean, I don't know, maybe it's not the end of the world. There's only like 10 junctions or something, but that's what you do. Are there other questions? All right. So we're still in chapter 12. We're learning how to use the specific energy method to answer lots of questions like, what does the water do when there's a choke? Or what does the water do when the channel gets wider? So neither of those could be answered with Manning's equation. Manning's equation only tells you what happens when conditions are steady and uniform. But if there's some sort of a disturbance that causes the flow to deviate from steady uniform flow, we need to use other methods like specific energy analysis. So this is where we left off on Wednesdays. We were talking about what happens if the step up is getting progressively taller. So the delta Z is small, no problem. The water will just adjust accordingly. It gets a little bit taller, that just changes the downstream depth a little bit further. And in this case, what it's doing is it's reducing the downstream depth. Because in this illustration, we're assuming that the flow at location 1 was subcritical. And that's what subcritical flow will do if you introduce a step, is it will cause the water to flow at a higher velocity and lower depth after the step. And we looked at the specific energy diagram to explain why that is, but that's what happens. And there's some maximum step height that takes us kind of to a critical threshold. The maximum step height, as delta Z gets bigger and bigger and bigger, eventually it gets so big that if we made it any taller, then the water wouldn't be able to get up over that obstacle because there's not enough specific energy upstream. There's only so much energy at 1 to push it over the obstacle. And if you make delta Z bigger, then you're going to induce pooling at 1 or choked flow. It's just there has to be an accumulation of additional energy upstream to push the water over the obstacle if the delta Z gets larger than that critical step height. So what happens is at the critical step height, at delta Z sub C, that's the step height that's associated with critical flow over the obstacle. So Y sub C is the critical depth. So it's flowing at the critical depth just at that last moment before choking occurs. And that's associated with the minimum specific energy, which is the least amount of energy that can be used to convey water through a channel of a given geometry, like a certain width at a certain flow rate. So this is what happens when we exceed it. When delta Z gets larger than that critical step height, then the water gets deeper upstream. So all of these previous changes didn't cause the headwater to change. Headwater is the water upstream. So the headwater, the depth at location 1, it wasn't changing in this first case, the second case, the third case. The only thing that was changing was the depth downstream in the tailwater. Now, here in this fourth illustration, we exceeded the critical step height, and so now finally the headwater is affected. And what happened was the depth had to increase so that there would be enough energy to push the water up over the obstacle, and then it's going to continue to flow at the critical depth after the obstacle. So you'll notice in these first two figures it just says Y2, 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 but then look in the third figure. Instead of Y2 it says YC, because it's flowing at the critical depth when we get to that critical step height. So, I mean, the depth at location 2 is the critical depth when you're at the critical step height or beyond it. So this fourth illustration is just showing when you're beyond the critical step height, you forced pooling upstream, so the specific energy at location 1 goes up and up and up until there's just barely enough specific energy to push the water up over the obstacle. So does everybody understand this so far? Why the water is reacting the way that it does? It's just, is there enough energy to get over the obstacle or not? That's what it boils down to. And if there's not enough energy to get over the obstacle, then water will accumulate, it will pool, the water depth will increase at 1 until there is finally enough energy to get over the obstacle and continue flowing at the minimum specific energy. You need to understand and be able to explain this, like a week from now. Okay. Now, as a reminder, if you have a rectangular channel, no, actually, I think it is true even for a non-rectangular channel, that when you are flowing at the critical when conditions are critical, depth accounts for 2/3 of the specific energy, and velocity head accounts for 1/3 of the specific energy. And having that 1/3, 2/3 relationship just makes it easier for us to calculate the minimum specific energy. Because if we happen to know the depth, the critical depth, we can just multiply that by 1.5, and then that gives us the minimum specific energy. So here's our specific energy diagram that was showing each of those 4 cases. Like when we had a small step height, a little bit larger of a step height, and how the depth got shallower downstream from that. When we had the critical step height, which was associated with the minimum amount of specific energy, but then if your step is larger than the minimum specific energy, we're not on the specific energy diagram anymore. So there is no alternate depth that is on that figure for delta Z sub D. So it would have to cause pooling, which is a new depth upstream. So here's just a zoomed in look at that 4th case, because it's really important that you understand the terminology here. Y1 was the original depth upstream prior to pooling. Y'1 means how deep the water got after pooling. Now, who can explain why pooling occurs? Who can kind of like restate or summarize why the water pools at 1? Garrett? You got it? Why does the water pool at 1 in this case?
Because the step height is at the critical height,
Mhm.
and there's not enough specific energy for the water to
Good.
go up, so it pulls.
That's right. Yeah, delta Z was too big. It's either at or beyond the critical step height. So there's not enough specific energy to push the water over the obstacle. So this original depth, Y1, it wasn't deep enough. There's not enough energy there. So what the water does is the water accumulates behind the obstacle a little bit. Like the water gets deeper and deeper. And so what is that effectively doing? When Y'1 is the new depth, that means that there's now more specific energy at 1. So it gets deeper upstream of the obstruction until energy accumulates that is sufficient to push the water over the obstacle. So Y1 was the original depth, and it's this dashed line here. It's the depth before pooling occurs. And Y'1 is the depth after pooling occurred. So then, by inference, you should be able to understand that E1 is the specific energy before pooling occurred, and then E'1 was the specific energy after pooling occurred. And then downstream, the water is going to flow at the critical depth. Like, why will it flow at YC? Because that's the most efficient depth. It's the most efficient depth because it's the depth that has the least amount of specific energy for a certain flow rate. So think of it as currency. Energy is available at 1 and required at 2. How much energy is required at 2? Well, you have to have enough energy to get over the step height and enough energy to flow at least critical conditions, because critical conditions is here the least amount of specific energy for a certain amount of flow rate. So this specific energy diagram, it's all the same Q. It's all the same flow rate. It's just a bunch of different depths for the same flow rate. So for the same flow rate, which depth is associated with the least amount of energy? So energy is on the x-axis. It's the horizontal axis. On this curve, this is the point of minimum specific energy. And it's the critical depth that's associated with minimum specific energy. So another way to think of that is it's the most efficient depth. Efficient being in terms of the least amount of energy that is capable of conveying a certain flow rate. So let's take it to a specific example. Let's consider this case of what if we had a channel that's 2.5 meters wide and 0.9 meters deep, and we're trying to put a flow rate of 4.25 cubic meters per second through there. Okay, so that's upstream at location 1. That's the headwater before the change, before some obstruction. What happens at location 2 is that we're going to put in a step. We'll consider what if the step height was 0.05 meters. We'll just find out what's the new depth downstream after encountering that step. And then in part B of this example, we're going to answer the question, how tall could the obstruction get just before choking occurs? Like, what's the maximum delta Z that could be tolerated without choking? So what I'm going to do is I'm going to pause and ask you to calculate a few things. Calculate the velocity at location 1. Calculate the Froude number at location 1. And here's the formula for the Froude number. This may look a little bit different than what's in your printed notes. I just substituted in the general form of the Froude number equation. Find E1, and E1 is the velocity head plus the depth. So just do steps 1, 2, and 3, and then we'll go through step 4 together. Feel free to start on it. This is the equation that you use for it. But we'll do step 4 together if you don't get that far. But 1, 2, and 3 I'd like you to do. Okay, over on the whiteboard on the right side, I've got the velocity, Froude number, and specific energy, all of those at 1. So the velocity at 1 should be 1.889 meters per second. Froude number, we calculate to be 0.636. Here I calculated it here using a slightly different formula, but 0.636 is the Froude number. And then the specific energy is going to be the velocity head plus the depth, and so the specific energy is 1.082 meters. So everybody get those same values for the velocity, Froude number, and specific energy? Why did we bother with the Froude number? Anybody, like foreshadowing, anybody recall why we want to know what's the flow regime at 1? Fred, do you know?
Check if the flow is subcritical or not.
Good. We want to know whether the flow is subcritical or supercritical, and why is that? Where's this all heading?
So you can determine Y2.
What's that?
So you can determine Y2.
So you can determine Y2, and specifically, like, how will the Froude number allow us to, like, what's going to be the if-then kind of decision point we come to? Do you remember?
If it's subcritical, it's more than YC.
Okay. So if it's subcritical at 1, then the flow will continue to be subcritical at 2. And that allows us to choose, because this is all headed towards some cubic equation where we're going to have 3 roots, one of which is negative, we discard, the other 2 are positive, but we don't know which of those roots to select unless we know the flow regime at 1. So that's why we got the Froude number at 1, was so that when we solve this cubic equation, we'll be able to know which root to select. Who's got a Casio calculator and knows how to solve this equation? I know how to do it on the HP, and I could probably figure it out on the Casio. I may have one in a drawer somewhere. What's the process? Like, what buttons do you push on the Casio to find the roots? If our equation is y2 cubed minus, let me bring up the equation on the screen here. So here's our equation. Oh, I can't highlight it like I could in Adobe. So here's our equation. What buttons do you push?
You go to mode.
Mode.
And then 5, which is equation.
Mode 5.
And then 4, which is the cube root solver.
Mode 5 equation. 4 is the cube root solver. And then do you just put in like
The coefficients.
the coefficients? So like 1 and then minus 1.0319. And then 0, because there's no y1 term, and then 0.1473,
And then you just press enter.
and then enter, and it solves the roots. Okay. So how many of you are using Casio calculators? Any TIs? Everybody's Casio? All right, so everybody here, do you have your Casio? Like an engineer without a calculator, you might as well be naked. Like, I'd rather have you come to class naked than come to class without a calculator. It would be, like, less prepared. But luckily, I don't think that's the case. Everybody's got their calculator. So solve this one. So let me write it on the board again. It was mode 5, and then 4, and then type coefficients.
Yes.
Okay, so this is the equation we want to solve. This equation here. Mode 5, option 4, and then you're going to type the coefficients, which are 1, negative 1.0319, and then 0, and then 0.1473, because this is like cube second, first power, 0 power, and then enter. Cameron, did you get it?
No, I'm going to have to come to class negative or something because I do not have my...
You don't have your Casio?
No.
Eee.
I do, so doing these, does it work with Wolfram Alpha, like for these ones? as well?
Yes, you can solve it with Wolfram Alpha, but not in the exam. In the exam, you can't use Wolfram Alpha. You have to be able to do it on a calculator. Noah, did you get it? No? So what the roots will end up with are 0.329 as the negative root, and then the two positive roots, 0.557 and 0.804. Did you get those? And so the one that we select is the positive root because that's the one associated with subcritical conditions. So the final answer here is, like if the question was, what flow depth will occur when there's a step up of 0.05 meters? The new flow depth would be 0.804. So the water originally was going at 0.9 meters. It encounters the step, and then after the step extracts some specific energy. By the way, the reason why we have the minus here, the minus is on the left-hand side, is because there's less specific energy at 2 than there was at 1. Because the amount of specific energy at 1 is being reduced in the amount of the step up. So after the step reduces 0.05 meters of energy, then what's left is having a flow depth of 0.804. So then, what is the maximum obstruction allowed before choking? So what we do there is we say, we know just before choking occurs, the water's flowing at the critical depth over the obstruction. So you say, let Y2 be YC. So that's what we're going to do for part B. For part B, let me write this on the board. By the way, I didn't say you had to come to class naked. Let's not make that, there's no mistakes there. I'm just saying the calculator's more important than clothes. Because you could always just go get some paper towels, but they don't have calculators in the bathroom. All right, so for part B, the situation is let Y2 equal YC. Because when it's just about to choke, the water's going to flow at critical conditions over the obstruction. So, like, what was our specific energy equation? It was y1 plus the velocity head, so velocity head v1 squared divided by 2g, minus delta z is equal to y2 plus the velocity head, q squared divided by 2g a squared. So now, this is unknown. Delta z max is the unknown, but we're just putting y2, we're substituting in the critical depth. So let me show you what that looks like. The critical depth for this rectangular channel we can find using this equation. Now what's the warning I've given you with this equation, which utilizes the flow per unit width? What's the caution here? It only applies for a rectangular channel because remember, flow per unit width is basically saying, how many cubic feet per second are you getting for each 1 meter of width? So if flow per unit width is Q divided by B, then that doesn't really make sense like for a triangular channel. If you've got a triangular channel, each meter of width has a different flow area. Whereas here, every meter of width has the same flow area. So only use this equation, which utilizes lowercase q, if you have a rectangular channel. For this example, we do. So if the critical depth is 0.665, then we're saying let the downstream depth be equal to the critical depth. And if that's the downstream depth, then we can find out the velocity head. So the specific energy equation is, you'll see here I moved the Z max over to the right-hand side of the equation. I don't know, it doesn't necessarily belong there, but we've got the specific energy at 1, the specific energy at 2, and so delta Z max is just the difference between the two. It's how much extra specific energy there was at 1 compared to the specific energy, the minimum specific energy that's required at 2. Remember that critical conditions are the most efficient flow conditions. It's the flow conditions associated with the minimum specific energy. So what we're saying is you can make the delta Z larger and larger and larger, but the biggest you can make it without inducing choking over the obstruction, this maximum is the condition that's associated with critical flow over the obstruction. So in example A, in part A of the example, the step height was 0.05 meters, and that didn't cause choking. Here what we're saying is it could go as high as 0.084 meters, but then anything above that, choking would occur. Okay, so any questions on the example that we looked through? To summarize some of the big ideas here, the maximum constriction forces critical flow. So that step height that's as big as it can be without causing pooling is the one that induces critical flow over the obstruction. And so critical flow is associated with the minimum specific energy for a certain flow rate and channel geometry. It's the most efficient depth. And if you go beyond that, if your constriction, meaning the height of the obstruction, if it's larger, then choked flow will occur. The upstream depth will get deeper in order to generate enough specific energy to overcome the obstruction. And what that means is that if you had houses along the river, then the water depth could get deeper than it was before. And that's why regulators get really touchy about you doing things like putting a culvert into a channel. Because if you put a culvert into a channel, you're potentially choking the flow. And if you choke the flow, then that could cause the water depth upstream of the culvert to be higher than it was before. And so you could be threatening people who previously their house didn't get flooded. But if you suddenly choke the flow through the channel, now all of a sudden during a heavy rainstorm, the water's going to be deeper than it was before because some obstruction downstream is choking the flow. So this has real world consequences. I know that we've just been doing like a lot of math, but the real world is that there are a lot of things out there that can constrict flow, whether it's a tree falling down across a channel. So that's like this is a fallen tree that's now in the bottom of the creek. And so what is the water doing when a tree falls across the creek? Well, potentially it just flows over the obstruction and there's no harm, no foul. You know, maybe there's no choking. But above some maximum step height and choking occurs, and then you're going to have an accumulation of specific energy. And so that could cause the water to go out of the banks compared to where it used to be. So let's look at kind of an extreme example. Let's say water's flowing along at 10 feet, and suddenly we drop an obstruction in that itself is 10 feet deep, 10 feet high. So obviously, if you put a 10-foot obstruction into a channel that water's flowing 10 feet, there's no way it's going to be able to flow over that obstruction without pooling. It simply, it can't. So it's going to have to get deeper. So here's the initial depth, y1. Y prime 1 is the new depth after choking occurs. Why does the water flow at the critical depth over this obstruction? Ethan, do you know why the water flows at the critical depth over the obstruction? Anybody remember? Because it's the most efficient depth. Like all of us, you know, like water is similar to us. It'll do the bare minimum. I do the bare minimum, right? That's engineering. Like, the essence of engineering is do the bare minimum, because if you do more than that, it's not efficient. Like, you wouldn't, I've heard the saying, anyone can build a bridge, but only an engineer can build a bridge that just barely works. You know, like, you want it to just barely be strong enough to carry the load, because if it's much, much stronger than is needed to carry the load, then you wasted a lot of money on steel that didn't need to be there. So here, why would the water flow at anything other than the critical depth? Because the critical depth is the most efficient depth for a given flow rate. So the reason why pooling occurs and it stops pooling once the water is able to flow at the critical depth, because the critical depth is associated with the minimum amount of energy required to get the water over the obstruction. So that's why it flows at the critical depth. Now, let's consider this example. What if the channel is 10 feet wide, so that's the distance into the page, 10 feet, B. It's carrying 500 CFS. The initial depth was 10 feet. How deep would it get? So the process we'd go through here is, first of all, find out how much energy is required to get over the obstacle, and then compare that to how much energy is available initially at location 1. So the question is there enough energy available at 1 to get over the obstruction? Well, we already know just by looking, like just plain logic tells you, no, there's not going to be enough energy at 1 to get over that obstacle if the obstacle is as tall as the water depth. So we kind of already know the answer going into this example, but let's just see if the math bears things out. We're going to find out the effect of the choke here. So find the total energy required. E required is the minimum plus the delta Z. Because we're a little bit pressed for time, let me just illustrate these calculations for you. So we want to find the minimum specific energy. So the minimum specific energy is that which is associated with the critical flow. So here I'm finding the critical depth is 4.265 feet. That's the critical depth. And you'll notice, by the way, since we're in traditional units here, I use 32.2 for G, because we're in feet in this example. So the minimum specific energy is 6.4 feet. So that's the specific energy that's required. And so the total energy that's required to get over the obstacle is the delta Z, the 10-foot obstruction height, plus the minimum specific energy of 6.4 feet. So that tells us that the amount of energy required to get over the obstacle is 16.4 feet. So there's got to be 16.4 feet of energy before the water's going to flow at steady conditions over that obstacle. So how much was initially available at 1? Did we have 16 feet of energy at 1 before choking occurred? So how much was initially available? The specific energy is the depth plus the velocity head. And velocity head we can express a lot of different ways. It can be v squared divided by 2g. Velocity head can be expressed in terms of q squared divided by 2ga squared. Or it could be lowercase q, flow per unit width, squared, divided by 2g y squared. That just takes the b term, the width of the channel, out of the velocity head. So here, I use that third method of calculating the velocity head, flow per unit width squared, divided by 2g depth squared. So how much energy was initially available at location 1, upstream? Well, there's the 10 feet of flow depth plus whatever specific energy is there. Not much. The specific energy is only 0.388 feet when we take the specific energy into account and add it to the depth. Basically, there's 10.38 feet. So E available is 10.38 feet. And E required is 16.4 feet. So to get over this obstacle, we need 16.4 feet of energy. There's only 10.3 10.4 feet of energy before any pooling occurs. So that's not enough. So choking will occur. So the answer is yes. Since E required is greater than E available, choking will occur. That's what we kind of already knew. We knew that you wouldn't be able to get water to flow over a 10-foot obstacle when the water depth is 10 feet. It's going to have to pool to get over that obstacle. Common sense tells you that. So, and the numbers bear it out. We compared E required to E available. E required is larger. So pooling occurs. So now the question is, what will be the new depth? Like, how deep should the water get to overcome that obstacle? So it's just specific energy analysis again. Let me write this on the board. Specific energy analysis in this illustration where the water depth has to pool, we know that it's going to be flowing at y prime 1. That's the new depth. And the velocity head after pooling is going to be q squared plus 2g y prime 1 squared. So this is the velocity head after pooling, and it's going to be equal to the E required. So it's going to be equal to 16.398 feet. 16.398 feet. So the water upstream is just barely going to accumulate enough energy until it achieves the minimum amount to get over the obstruction. And what we already found was the minimum amount of energy to overcome the obstruction is about 16.4 feet. So the new depth is going to be, this turns into a cubic equation. So this becomes a cubic equation, which is y1 prime cubed minus 16.398 y prime 1 squared plus 38.820 is equal to 0. And then we get some roots. Now, obviously, the new depth it's going to have to pool to is 16.25 feet, because 1.6 feet, that wouldn't be pooling. That would be, its depth would be lower than originally. And the water's not going to have its depth go down upstream when you choke it like that. It's going to get deeper. So that's how we know which of the roots to select. So the water's going to have to get to be about 16 feet deep to overcome that obstacle. All right. Any questions about what we do to solve for the new depth after choking occurs? Basically, we set the left-hand side of the equation, which is the conditions upstream, equal to the minimum required specific energy. So we calculated how much minimum required specific energy there is by saying we know it's going to flow at the critical depth at the downstream location. So the required specific energy is the height of the obstacle, delta z, plus the minimum specific energy, which is the velocity head plus the depth at 2. All right, so here's an extension of that. What if, instead of 10 feet, what if it was only 3 feet? Is that going to choke the flow? So the way that we know if it chokes the flow when the step height is only 3 feet, this is the same conditions. This is like the same situation. Originally the flow depth is 10, same flow rate and everything. Will it choke if the step is 3 feet? Well, in a case like that, we're just going to compare the required specific energy to what's available. And we earlier found out that the available specific energy at 1, this is available at 1, was 10.4 feet. And so how much is required at 2 if the step height is 3 feet? All right, so the required is the minimum specific energy plus the delta Z. That's the minimum amount of energy that's required at 2. And so the minimum amount of specific energy that would be required at 2 would be 9.4 feet, because we're just saying, like, the least amount of energy would be if the flow was going at critical conditions over obstacle at 2. So critical depth, and the minimum specific energy is 3 halves times the specific towards the critical depth, and the required specific energy is the delta Z plus the minimum specific energy. So there has to be at least 9.4 feet of energy available to get over that obstacle. And we found that what's available previously, 10.38 feet. So no choke will occur if the step height is 3 feet, because the amount of energy that's available is greater than what's required. So we're good. 3 feet is not going to choke the flow. Like, how high could the step height get? Well, to find out how high the step height could get, you just say the maximum delta Z is the difference between available and the minimum specific energy. So if it gets any taller than 3.988 feet, then the flow will choke at 1. The water would have to get deeper to overcome an obstacle that's that tall. Okay, so preview of where we're getting next time when we get together. We're going to look at what happens when the channel gets narrower. When the channel gets narrower, then your flow per unit width changes because B is smaller. And if the flow per unit width changes, then the critical depth is going to change when you make the channel narrower. And so if you've got a different critical depth, then you're no longer on the same specific energy diagram. And so if you make the channel narrower, you're increasing the flow per unit width. And what that does is it pushes the specific energy diagram to the right and up, because your flow per unit width is larger, the critical depth is larger. So this is showing the the specific energy diagram when the channel was wide, and then this other diagram is showing the specific energy after the channel was narrower. So we'll talk more about that when we get together on Monday. We're out of time for today. Remember that what you've got on your plate is an assignment that's due by the end of the day, by 11:59 p.m. Submit that, and then the design project Monday before class.